Geometric isomers. These work around the double bond of a carbon atom. So we substituent, when the more dominant substituent is arranged differently, it creates geometric isomers. What are you looking at, Jess?
Aren't you supposed to have like different functional groups on them as well?
That's only when you're going into EZ. With cis and trans isomerism around the double bond of a group, the substituents need to be the same or similar enough that there's no real difference. For example, butene, that's the word, and it's got two stereoisomers. The first stereoisomer is here. This is the cis isomer, and it's also Z, but we'll move on to that in a minute. And this is the trans isomer. Okay. So cis isomers occur when two of the same substituents are pointing in the same direction around the double bond, and because they're cis, because they're on the same side. Trans is when they're pointing in opposite directions, like so. Now, you may be wondering what the E and Z there for. They are referring to E and Z isomers occur when the double bond is surrounded by surrounded by functional groups that aren't similar or the same, such as, for example. Now you may be wondering, how do we define the geometric isomer when we have 4 different functional groups? I'm glad you're asking that question. What we do is we take the molecule with the largest atomic number on the end of the branch, and that will take dominant preference over whether the molecule is E or Z. So we'll remove this. Now, in this molecule here, we have Cl on this side of the group, which is the largest molecule in the group, that largest substituent. So that will take priority here. And over on this side, the F takes the priority as well. So this molecule here, the two substituents are pointing the opposite direction. That is actually classed as an E geometric isomer. So I'm not going to bother naming that because that's just confusing. Now, if we look over at this one, we just wipe that all away. This one is a Z isomer because now the two largest substituents are sitting on the same side. I don't know why it's E and Z. It's just
German.
German, there you go. Thank you, camera lady. You are very useful. Okay, now I was going to do something. I was going to very quickly explain a quick principle that people always wonder about.
Can I make a point on the German?
Yeah, it is a very good point on the German. Thank you very much. Now. Okay, now you may be wondering, which side here, these are still both E and Z isomers, but you may be asking why, because two of the substituents seem to be fairly similar besides one double bond. The double bond is confusing. Long story short, the way I like to think about it is, there's more lines on the double bond, so that means it's higher priority. I should mention double bonds are higher priority. So double bond takes higher priority because the way Joel described it, he said there's two dummy carbons on the double bond, but I just like to think of it as more lines, higher number. So when you're thinking of it, just look for the double bond. If there's a double bond there, then that is the higher priority. Yeah, now I will be giving you an example now. Okay, now, please tell me if that is E or Z. Give me a little break there so they can figure it out. Yeah. If you got Z, then you're wrong. The answer is actually E. Now, the reason why this is E is because if we look at this side, the easiest side, the chlorine here is the highest, has the largest molecular mass. So even though this here is a much longer chain and has a fluorine attached, the chlorine will take priority. Now this one here, if you did notice, if you count up all the carbons, you'll see that both branches have 11 exactly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and one oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and one oxygen. So again, you have to ask which one's going to be higher priority if they're both the same. This one here has a double bond, so more lines, higher priority.